Welcome, welcome to the third lecture from chapter number 4. We are studying fabrication of CMOS ICs, and in this lecture we'll study about metals, the use of metal in fabrication of CMOS ICs. Metal is mostly used for two applications: to make interconnect lines and to make Silicides. Right. Shortly, we will see what are interconnect lines in a CMOS, in CMOS fabrication, or in a CMOS layout. What are interconnect lines and what are silicides? Right. Aluminum is the most widely used material for many applications within CMOS ICs, including these interconnect and silicides, and it adheres well. The first advantage. The second advantage is it can be given different shapes, because interconnect lines can be of different shapes, mostly mostly containing angles of 90 degrees, like this or like this. So they are mostly bent on 90 degrees, but they can be of different shapes. So patterning requires. So the metals are patterned well. Which metal? The aluminium. Aluminium metal has an advantage that it can be patterned well, and it's the most commonly used material, and it adheres well to other semiconductor-based materials that we use in the fabrication. Aluminium has a very small resistivity, rho is 2.65 micro ohm centimeter, and it gives us a sheet resistance. A sheet resistance means that, did we know that the formula for R is rho L over A? Rho L over A, and this A in the denominator can be written as T times L. So if this L cancels with this L, if we have a sheet, whose length is the same as its width. So if the length is kept as the same as the width, so this small cube has a resistance equal to the sheet resistance. So this L cancels with this width, because the L and the width, the length and the width, L is equal to W. So they cancel each other, and we are left with rho over T. So sheet resistance is resistance of a cube having length is equal to width. So RS is 0.265 ohm. It's quite small for aluminium, and this is the interconnect line. For example, if you want to connect this in this layout, you want to connect these two terminals with VDD. So this red line that we use is the interconnect line. But aluminium has some disadvantages, and perhaps the biggest disadvantage of aluminium is the term electromigration. Electromigration occurs when we have J crossing J max. What is J? J, we already know J is current density, current per unit area, I over A. So in a given aluminium bar, if the current per unit area increases from a certain value J max, so along with the electrons, some molecules also transfer from one part of the bar to the other. This leaves voids or gaps on one side and small hills on the other side. The hills are called hillocks, and the gaps are called voids. So this D-shapes the metal, and it's an undesirable effect. So how to mitigate, or how to address this problem, is by mixing copper with aluminum. Copper itself has a resistivity smaller than aluminum, but if we add it with aluminum, the resistivity increases a bit. in a bit, then the increase the resistivity of this alloy is a bit higher than the resistivity of aluminum. It's 2.65, and that of alloy is 3.5, so it's a bit higher. So this is a disadvantage. Electromigration can be avoided with the help of this mixing, but it introduces another problem, that the alloy has a resistivity higher than the resistivity of aluminum. So it gives us a sheet resistance for the same thickness. It gives us a sheet resistance a bit higher than that. So it's almost 32% higher than the sheet resistance of aluminum alone. So we have to make a compromise. Right. The other application for metal is silicide. Conventionally, aluminum is used as a metal. We have studied in our earlier lecture that why a MOS is called MOS, because this is metal. This OS comes from silicon dioxide, the insulator layer in between, and S comes from semiconductor. But in modern VLSI design, it is replaced. In modern VLSI design, the metal is no more used to fabricate gate, but it's now the poly. A material that is fabricated by introducing more silicon atoms on amorphous silicon dioxide. We studied in last lecture. So aluminum, another disadvantage of aluminum is that it has a low melting temperature, and high temperatures are common in modern VLSI design. So metal use of aluminum to fabricate gate is not a good choice. Poly is the new choice, is the new CMOS standard, but poly has a disadvantage. Oh, everything has some advantages and disadvantages. Poly has a disadvantage. The sheet resistance of poly is quite high, 25 to 50 ohms compared to aluminum. And we studied that sheet resistance of aluminum was less than ohm, 0.265. And here we have a sheet resistance 25, almost 10 times, 100 times, 100 times higher than the sheet resistance of aluminum. So how to address this problem? It can be addressed by using a titanium or platinum, thin layer of titanium or platinum on top of poly. This decreases the overall resistance introduced by poly. Right. So copper is another choice for interconnect materials because the resistivity of copper alone is smaller than the resistivity of aluminum, which is good because we are looking for a material that has a very small resistivity, ideally a zero value of resistance. So this is good that resistivity of copper is less than resistivity of aluminum. So using copper as an interconnect material instead of aluminum it seems to be a good choice, a better choice, but everything has some advantages and disadvantages. Patterning copper is difficult, giving it shapes like this, box, a right angle turn on this, a U shape pattern, making these patterns, which are quite common in CMOS layouts. This patterning is difficult with the use of copper. So it's a disadvantage, and it requires specialized techniques that we call damascene, and we will study about damascene in our upcoming lectures. That's all for this video, and we will continue studying IC fabrication techniques in our upcoming lectures. Thank you.